Hi guys, the back side with the coffee. Yeah, so I'm Mohammad Abdul, so I'm working in Intel Shannon here on a Hyperscan project. And so we start like with this all big data talks we are dealing with here. So with internet traffic is growing day by day, and definitely we need to look into, we need to monitor for several purposes, like operators want to monitor them, regulators want to monitor them, bad people wants to monitor them. So we need to deal with all those things. So we use a very common thing like a DPI approach. And when we have this internet traffic, when you look for some specific things with a very specific format, we can use like a parsing. We strip the headers, we look for some particular form fields or something, and we decide what to do, or what kind of traffic is going on, what kind of application is going on, and what we should do, how to do billing, how to do other things. On the other hand, like if we don't know exactly what's going on, and we just know some roughly patterns or something, so we use some pattern matching or regular expression matching on those packets, because sometimes some networks are under attack, some worms, network worms, or DDoS attack or something going on. So we don't know exactly what kind of pattern, or how long the packets or spans or something. So we have to deal with those things. And so there are several ways, like we can look for some fixed string, we can look for some regular expression. So if we are looking for some strings with like 1,000 strings with all starts with A, so you need definitely we need some 1,000 places. It's very easy to match, but we need long space or something to manage. But if you're looking for A starts with A dot star, that's it. We just need only one space to manage. But definitely it's dot star. I don't know how long it will be the string, so it's a very high computation power is required. So we use two kinds of things, and here to do this pattern matching. And this pattern matching actually, you can say, in the heart of all the security applications nowadays. And so whenever we have this very complicated attacks or complicated scenario comes, we need to scan those packets more intensively. And the more intensively we use more CPU, more cycles, more memory, everything. So we have to be very, very efficient. So traditionally we use this fastest way is hardware. So there are a lot of people do this hardware-based approach, like FPGA-based approach. We also tried, some other companies also tried. And at the same time, it does also scale in time, but doesn't scale over for long run, because the scenario is so dynamic that we need to develop it. The maintenance cost, development cost, time to market cost is really, really high. So we need to find something which is we can adapt very quickly. So we know that the software is the best solution. If we can develop something as software-based pattern matching, it can scale, it can update, and we see that we have a very dynamic environment with all those fields coming. It's very quick, rapidly changing with all those cloud, wireless, big data, routing is everywhere. We have to update this. So how we solve this pattern matching problem with some software? So the solution is, ta-da, Hyperscan. So Hyperscan is this pattern matching engine, which actually does this fixed string matching, regex matching, very efficient, and with a very low latency, and it compiles very fast, like 20 seconds or less than that. You can, with thousands of patterns and all those things, it's super fast. And also it uses very little memory. So, and when we had this, it uses, exploits all the CPUs, whatever the features it has. It scales all the IA from Atom to Sandy Breeze or whatever we have now, Skylake. We just is under. So we use the Xeon, and it also can be, it runs in all the software, all the operating systems, like it's completely independent of operating systems. So when you have the Hyperscan there, it can run on OS, normal OS, or it could run on Hypervisor, it could run on the VMs, and or this could be service chained from one VM to another VM, or it could be service chained from one hypervisor in the hypervisor. And when we're using this, the operators or OEMs, they use this library to tackle all those problems like intrusion detection or firewall, unified threat detection, content filtering, all those sort of things. And it does run all those like right now. It's not only the limited operating systems I listed here, there are also other operating systems. And it runs on all this hardware, like besides Intel, it also runs with MIPS, and it also runs with Power and Mac. It all supports all those hardware things. Yeah. The current release, it supports this 32-bit, 64-bit both, and it's very portable. And current release of Hyperscan is actually this version 3.4. So we're planning for the next release very soon. It is coming very soon. So how exactly it works actually, or what Hyperscan is actually, or how it works, if we want to say, like we have some list of patterns or some I would say like regex there, or rules, signature, whatever you say. So we have those regex, or we parse them, we make some state machines. So we know the most common state machines are like this automata, which is like non-deterministic automata or deterministic DF, we call it just NFA, DFA thing. So we make those trees, or we make those state machines, and we convert them, we compile them in terms of bytecode, which is for all those patterns and all those things, so that it can be. So during the runtime or in the live network, we use those bytecode, or operator use those bytecodes, and looks for those patterns against all the streams that are coming in the network. And one of the most powerful property of Hyperscan is it supports is streaming mode. So it's like a streaming mode, like when you have like some packets are coming. So if you have a block mode or something, like you have all the packets here. It's easy, like if we're looking for some particular pattern, and if we don't see that pattern, maybe we have to go back, or something like we call it backtracking or this kind of thing. Then we need to look for the whole data should be there in hand. But when it is streaming mode, you know, this each packet can contain only 1 byte. So if you are looking for some pattern, so by spanning thousands of bytes, so we have to store those. We have to keep those history in some buffer. But the Hyperscan, it has some efficient features, like efficient tricks, like it doesn't need to store all those thousands of packets or something. It maintains some smaller amount of history, and it does whatever it needs to be done efficiently. And when we do this, like if I want just give you some example of like this kind of engines, just some more flavor. Okay, so let's say we have some patterns, like we are looking for some bad guy with a starting name like badge, then not Jet something, it could be 0 or more, not Jet, then it ends with bar something. Then for this pattern we make some engine. It could be non-deterministic engine, it could be deterministic, because non-deterministic engine in terms of like you can say it could be 0 or more non-Jet character. So you can say like when you have these transitions, when you have this, okay, it's very easy, B, A, Z, so you know how it works. So this character is like an anti-character or anti-symbol, we can say. So it means without even scanning any character, it can jump from one state to another one. Okay, that's great. Yeah, that's nice. So it means when I am at like state 4, we have some non-deterministic environment. Like I don't know whether I should jump to state 7 or I should jump to state 5. Yeah. So this is the environment. So on the other hand, when I convert this engine to a deterministic engine, so you see that here I know that only if I see a character B, I just 6. If I see a non-get character, I just jump 5. So this is how it, very simple. It's very simple technology, right? And when you have looking for this text, like when you have like, okay, we have a BA, we look for BA somewhere, then you see again B, and it fails, then what to do? We don't know. So we hyperscan, it creates some more simple, or actually a bit complicated. It creates some more DFA engines or something. Yeah, exactly. So that it doesn't stop, doesn't halt, it just keep scanning, and whenever it goes to these double rounded states, okay, I got some feature, I got something. So what we have here, we have we can put this in the Intel register or whatever the computer registers about this state. Like, okay, I need only 10 bits to keep this state information, and I need some table to list these transitions. Very simple algorithms. But when we have some pattern like this, and when you have I don't know how many states will be required. It could be like 10,000 states could be there, and we don't know how to store this we cannot accommodate them in a register or something. And then we have some features like bounded repeats, like it could be some pattern could be repeated 10 times to 30 times, and if we don't see them, how to backtrack them or something. So there are some mechanisms then. So we divide them, we chop them into pieces, make some small trees, then make some communication among them, make some tables among them, and that's how we build our efficient hyperscan. So how it does, well, in terms of efficiency, like if we have an NFA, is very, in terms of computation, is very high computation, but it's very easy to manage all those things. It's small, and
it doesn't blow.
It doesn't blow, right? Yeah, but when we have this DFA, it can be, because it's deterministic, it could be thousands of states over there. So it's always, we have some trade-off. But on the other, the hyperscan sits here. It handles all those problems very efficiently, and it really nails it down. And so in terms of like performance, we have some tier 1 VM signatures, 2 minutes, yeah. And some real-time traffic. So we use on top of like our Intel CPUs, like here 2-core, 4-core, no hyper-threading. Here 8-core, one like hyper-threading. There is a 18-core with hyper-threading. And we got some performance up to like 293 Gbps. This is pretty old benchmark. It's not up to the latest one. Latest is more than 400. So this is how it scales. You can see this. This is the line rate performance. How we achieve this line rate performance and all those things. So
how many megabytes?
Sorry.
How many megabytes? Signatures.
More than 10K. But I cannot tell you the exact number. More than 10K. The sky is the limit. So how we drive this? So I have only 1 minute. So how we drive this? We use all the IA. We have a lot of IA features to this. We use we use this dedicated L2 cache so that we can put this the engine tables in the cache residence. We don't have to just. But sometimes there is a cache fault there. But we try to put them in memory, so that it is very efficient. We also use a lot of intrinsics, like we use a lot of packed shuffle bytes, packed extract bytes. That's deposit. We use FBX2 large registers for these. These are the we use we try to squeeze all those IA, juice out whatever is possible. and we are still exploring more. So in the future you will see more and more performances coming there. Okay, thank you very much. Any question? Yes, please.
Maybe I missed it. Is the goal to make it as part of DPDK, like the SL libraries?
I don't know. Actually, right?
It's not, there's no current plan to make it part of
Yeah.
it. It exists as a separate project.
And so there is a website where we can...
Of course. You just you can if you Google with the Intel Hyperscan.
We can download Hyperscan from the...
No. It's proprietary. But you'll get some white papers and also some other reference. Okay, I know this is not interesting. Yeah.
Yeah, there is a plan to open source it, but it's not available right now.
Okay. So you have some hope.
All right, thank you very much.
Welcome. Thank you very much.